Okay, let's go ahead and get started for today. We're starting to run out of classes here, so we're not going to get through everything that I wanted to this semester. We kind of lost a week there in the middle, but we're going to get through what we can. We're going to switch gears a little bit from the kind of lower level stuff that we've been doing and the programming language stuff we've been doing and get back to something that's a little more conceptual. And today we're going to talk about liveness, which we've talked about in the past, but today what I want to do is talk about it in a little more specific detail. So what we're going to talk about today is this concept of deadlock and Livelock, and we're going to do so in a little bit more detail than we did previously. So let's go ahead and get started. All right, so the first thing here, as a reminder, there were kind of two aspects to correctness of some sort of program or concurrent system design. And one of them is a safety property, which said that nothing bad would happen. And bad things would be like corrupted data, incorrect output, incorrect function. And so the ATM machine problem that we looked at previously, where it loses a transaction, you do a concurrent update to the bank account balance, a deposit and a withdrawal, or two deposits, one of them overwrites the other. That would be a violation of safety properties. In other words, the system will do something wrong. Now, what the liveness property is, that means that something good will eventually happen. And if a program locks up and never produces any result at all, notice that's a different thing than a safety property. Safety property says that nothing bad will happen. It won't get wrong answers. This isn't a wrong answer. This is no answer at all because the system is locked up. So that would be a violation of liveness. If something like locks up, it can't continue, that's a liveness property violation. And there are kind of two versions of that. There's deadlock and there's livelock. We're going to focus on deadlock mostly today. We'll touch on livelock toward the end. Okay, so that's what we're going to focus on today. So first off, let's look at definitions of each of those. So deadlock is kind of you have some set of processes S, and it's deadlocked if every process in S is blocked on an event that can only be caused by another process in S. In other words, they're all stopped waiting on something from someone else, some other process, and all of the processes are stopped waiting. So on one of the other processes, it's in that same set. So in other words, there's no way that we can ever get them unblocked because nobody can make any progress to get unblocked. We're going to look in more detail at that here in just a second. Livelock is similar, except that we have some set of processes S, and what they're doing is they're repeatedly entering some same sequence of states. So they're doing something. They're not necessarily blocked. They're actively doing something. But the thing they're doing isn't really producing any useful work or any progress towards our goal. And then they repeatedly go through that same sequence or some subset of those sequences as they continue to try to do something but never make progress. Now notice that that's kind of the same as deadlock, but in deadlock the process is blocked. In livelock, they're actively repeating some sequence of events, never getting anywhere. So notice that those two are closely related, but not quite exactly the same thing. Okay, now let's start with deadlock, and we're going to focus on that for just a little bit here. So for deadlock to exist, there are four conditions that have to arise all at the same time, and those are required to have a deadlock state. So the first condition, processes have to claim exclusive control of some resource. And then that could be something like a lock. It could be something like a file handle in the operating system, or a socket from the networking system where they open it, it's theirs. It can't be taken away from them, and they hold it exclusively. It's something that can't be shared. So think of it like a program opening some sort of resource, like access to some particular piece of hardware. And while that process is using that hardware, no one else can use it. Or in the real world, you might think of it as there's a tool shed. Somebody goes into the tool shed, they take out the saw, they take it off with them to the job site. No one else can use that saw because it's now gone from the tool shed. All right, the second condition, processes hold on to resources while they're waiting for others. So in other words, they have a resource that they've taken, but they need another one. They're going to hold on to the original one while they wait. So in other words, I need a saw and a hammer. I have the saw. It's in my hand. I'm not going to give it up because I need it for my job. I also need a hammer. The hammer isn't in the tool shed. I'm going to stop and wait for the hammer to show up because I need both of them to complete work. But I'm not going to put the saw back because I need it. I'm going to hold on to that. All right, the third one there, resources cannot be taken from a process by force, meaning it's a non-preemptive resource. In other words, somebody can't just come and take something away from the process. If I'm holding onto the saw, another worker can't just come and grab it from my hand and take it from me. It's mine once I've picked it up. And then the fourth one is there's a circular chain of waiting. In other words, they're all waiting on something that someone else is waiting on that eventually leads back to the beginning of the circle to make this kind of circular chain of waiting. And note in that case that every process has to be holding on to something that another needs, but every process is also waiting on something that another one has. And that's where you wind up with a deadlock. You have to have all four of these conditions arise all at the same time, and then you'll have a deadlock condition. So notice that you could have these first three, but not the circular chain. I could be waiting on Joe that's using the hammer. When he's done, he puts it back and I get it. That's not deadlock. It only becomes a deadlock once you get that circular chain. Okay, now here's a real world example. And I've actually seen this happen right down the street, right down the, at the end of, I guess that's what, 3rd Street, maybe it's 2nd Street and Offner. There's kind of an intersection where the stadium is over here, but there's kind of a turn this way and a turn this way onto 2nd Street, a turn this way onto whatever street that is, Grant or something like that. But you'll notice that if we have too many people driving in each direction, and this person wants to turn that way, and that person wants to turn that way, that there is no way that they can make progress. They're deadlocked. There's no way that this person can ever turn. There's no way that person can ever turn. And the cars that are built up behind them can never move out of the way or go forward. So that's example of deadlock. Now, how does that meet the four conditions of deadlock? Because even a real world deadlock example has to meet those four conditions. So first off, exclusive control of the resource. So what would the resource be here? Well, the resource would be the space on the road. In other words, this car and that car cannot occupy the same part of the road because they would crash into each other. And they can't physically occupy the same space on the road at the same time. It's a violation of laws of physics. And so hold the resource while waiting. Yeah, well, while this person's waiting to turn left, they're going to stay there on the road. They can't magically disappear while they wait to turn left. They're stuck there on the road. Resource can't be taken. Well, I suppose that somebody could get out of this car and drag this person out of the car and put them in the trunk of the car and then shove it out of the way to break the thing. But the default situation is you cannot physically take the resource or shove somebody out of the way in the car without violating the law. All right, and then a circular wait, you can actually see that right here. These four are involved in the circular wait, but notice that just the four involved in the circular wait could be holding up others that aren't necessarily involved in that circular wait. So you can have the same thing in processes. But notice that all four of those conditions exist here. Exclusive control of the roadway. They stay on the road while they're waiting to turn. We can't make them get out of the way. They have to decide for themselves to move. And we're waiting in a circle. So there's a real life example of deadlock that it can happen. And I've seen happen when a event at the stadium lets out and there are a lot of cars coming this way and a lot of people going this way. Then you wind up with this being blocked off like that. Okay, now here's another kind of fun example that's been around in computer science for a while called the dining philosophers. And this example, we basically, the game works like this. We've got kind of a set of plates of spaghetti and the same number of forks. And in this case, we've got 5 of each. And then we have people sitting in front of the plate of spaghetti. So here I am at the top. We've got Jason and Dwayne and Jim, and Travis. And we're all sitting around I don't know if I'd call us philosophers, but we're all sitting around this table. And the rule is, in order to eat the spaghetti, we need to use 2 forks at one time. In other words, we got to kind of stab the spaghetti, kind of twirl it around with one while holding it on the other, and then take a bite. So philosophers think for a while. So we sit there and we think, and we're thinking, and we're thinking, and then we decide, you know what? I want to eat some food. So I pick up a fork, I pick up the other fork, and then I eat for a little bit, and then I put the forks down and go back to thinking, and then I basically repeat that until my spaghetti is gone. So in other words, think when you're ready to eat, pick up left fork or right fork, doesn't matter which one, but we pick up both of them. We eat for a little bit once we have both forks. We can't eat until we have both forks. And then we put both of them down when we're done. Now, this has not happened right down the street, unfortunately, but at least with us. But the idea here is that we want to do that. Now, if you look at it from the point of view of like, okay, what does it take to eat something? Well, when we're ready to eat, we pick up the two utensils, we eat for a little bit, we put them down. That seems like that should be totally fine. It seems like everybody could have this great meal experience, with the exception of we're sharing forks, which at least right now is probably not within social distancing guidelines. But the idea there, if you looked at the kind of process for each of those philosophers, or the sequence of how they go about eating for each of the philosophers, this makes sense. It seems like there shouldn't be any problem. But it turns out that there is a problem. So what could possibly go wrong here? So if you look at it, it seems like it makes sense. When you're ready to eat, you get the two forks, you eat, you put them down. But it can deadlock. So how can this deadlock? How could this get into a state where we're deadlocked? Well, if we think about that, everybody could become ready to eat at the same time. They could each pick up the fork, let's say, to their left or their right. It doesn't really matter. So I think this says left, but over here in the picture, I think I have it to the right. So everybody picked up the fork to their right. And you'll notice that once they pick that up, the next step in the thing, let's go back for a second, is to pick up the other fork when it's available. So in other words, they hold on to the one fork that they've picked up. They wait for the other one to be available, but everybody has one. They're all waiting, looking at the spot on the table where the other one should eventually show up. And they're going to be waiting there forever. So they're never going to get to the place where the other fork shows up because somebody's holding on to it waiting. So in this case, you'll notice that nothing in that sequence of rules back here allows them to ever put one down while they're waiting. They pick up one, they wait for the next one to be available. When it is, then they eat. In other words, they're all stuck right here waiting for that second fork to become available. Now, how does that fit the four conditions? Exclusive control of some resource. Well, they are all exclusively controlling the forks. Do they hold on to one while waiting? Yeah, they do. The resource can't be taken. Nothing in their rules for eating allows them to take one. And we definitely have a circular wait, because in this case, here's me at the top. I have this fork. I'm waiting for Jason to put that one down, but he's holding that one, waiting for Dwayne to put his down, who's holding onto that one, waiting for Jim to put his down, and Jim's waiting, holding on to his, waiting for Travis to put his down, and he's back to waiting on me again. So there's the circular wait going around in like this clockwise direction there. And we have all four of those conditions all at once at the same time. Now, it's possible that we could follow these rules and get totally through the meal just fine. It could work just fine. And this is another problem, again, with concurrency and with deadlock, is that running a program and having it work fine doesn't mean that it's correct. It doesn't mean that it's going to work fine every time. So we could go through 100 meals and all get through our spaghetti just fine, decide, hey, this process works great, but then at some point in time, we all try to eat at the same time. We all pick up the same fork on the same side at the same time. The fork, in this case, to our right. And then we all starve to death and die. So this would change into a bunch of skeletons around the table. All right, so the idea there is that testing can't find this. We've got to be careful about things whenever we have exclusive control of resources, holding them while waiting. Resources can't be preempted. And the possibility eventually of an emergent circular wait, we've got to be very cautious about how we write that code. Okay, now, how do we deal with that in our code? Well, we're going to look at three possible ways of dealing with that. And those are deadlock prevention, deadlock detection and recovery, and deadlock avoidance. And if we look at kind of the description of those, deadlock prevention basically is designing the system in such a way that one of those four conditions, let's go back and look at those for a second, one of these four conditions just cannot ever happen. So we're designing the system in order to do that. The second one, deadlock detection or recovery, kind of allows anything to happen, all those four conditions, including having them all happen at once. But when they do all happen at once, we're going to detect that state, and then we're going to do something to break that deadlock and then recover from it. So the idea there is, go ahead and let it happen, but if it does, then we'll have this contingency plan where we'll constantly be looking for that And if we see a deadlock, we're going to break it, and then we're going to go on about our lives. Deadlock avoidance is kind of like deadlock detection and recovery, except the difference here is that we're going to allow all 4 of those conditions to occur, but we're going to be careful about when somebody requests a resource, when we grant it and when we reject it. So in other words, we might have something available and somebody asks for it, and we think about what state that would put the system in. We say, you know what, even though this is available right now, I'm not going to give it to you because that could create an unsafe kind of state where deadlock is imminent. And so this one is kind of smart allocation of resources, where this is just designing the system to get rid of one of those 4 conditions altogether, so deadlock could never happen. This one is, hey, wild west, let it happen, and then we'll fix it when it does. All right, so let's take a look at each of those. Let's start off with prevention. So deadlock prevention is designing the system to eliminate one of those 4 conditions, or maybe one or more of those conditions. But there are some design options, like never allow exclusive resource usage. Now that in practice can be really difficult to do. For example, imagine somebody needing to have some resource like, I don't know, access to a tape drive to load things up that were backed up. You can't really have more than one process at one time sharing the use of that tape drive. So and same thing might be for the keyboard or the mouse. We might not want to have resources that don't have exclusive use. Another one might be network sockets. While there might be a lot of sockets available in the system, there's still a finite number of them. And we can't allow people to share the same socket, the same port address, the same thing, because one program would end up messing up another one. So this one kind of eliminates condition 1, but it's not really practical. All right, the second one, all resources are requested and granted all at once. That one actually could be done. You could have that. So when a process starts up, it says, I'm going to need this set of things to do my job. And either they're granted all at once or none of them are granted. So it's kind of an all or none. And notice that gets rid of the possibility of a circular wait, because you can't hold on to some, or actually also the second condition, you can't be holding on to something while waiting for another one. And if that's the case, you can never have a circular wait, because you'll never hold on to something while waiting for something else. So this one is a little more practical, but also notice that, let's say I need, that can also lower our kind of resource utilization, because let's say I have to have a hammer and a saw, and most of the day I'm going to use the saw, but then at the very end I just need to pound in one nail. I'm holding on to a hammer the entire day and I'm not using it. So this one can work, a little more practical than the top one, but it still lowers our resource utilization. The other one is releasing resources while waiting for others. In other words, if I go to the tool shed and I need the hammer and it's not there, and I have the saw, I have to put the saw back and then wait. So, and then I have to acquire them all again at that point. And that can also hurt resource utilization, because you could have people, a crowd of people, imagine sitting around and they keep picking up a tool, the other one's not there, put it back, pick up this one, put it back, but they might need a collection of them all at once, and they might not get them because they're all sitting there around the tool shed picking up and putting back tools. The other one is to create this kind of linear hierarchical ordering of resources, meaning that when you acquire the resources, imagine you put numbers on each of them. This is hammer, I'm going to call it 1. This is saw, I'm going to call it 2. And if I need a hammer and a saw, I always have to get the first one first and the second one second. If I only need the saw, that's okay to get that one, but because I don't need the hammer, but that eliminates the possibility of a circular wait as well. Now, notice that some of those can be impractical or cause the system to be more inefficient or less efficient, less capable of high levels of resource utilization, because we're putting these kind of hard restrictions on the way we go about getting things that we need for our programs. Okay, moving on to deadlock detection. The idea behind deadlock detection is we let it happen, and then we want to break that and recover from that when it does happen. So the first part of that is detecting it. So to detect it, the idea is generally to look at who has what, who's requesting what, and look for that circular wait condition that exists. So we're going to do that with this kind of looking for a cycle in our resource allocation graph. And if we look at the way we're going to model this, we're going to do kind of these boxes are going to be processes or tasks or threads, whatever you want to think of them as. But think about this as a separate process that's running. A resource is going to be a circle, and inside of that circle, I'm going to represent kind of an individual resource of type R1. So this might be hammers. There's one hammer that's available. If we had a tool shed with two hammers, we might have two little circles inside of there. So these are identical resources of some type, and this is how many of them there are. We have inside of there the little circle. Now, that would mean that a diagram like this is P1, reaching out, wanting one of these resources of type R1. It doesn't have it yet, but it wants that. There's one available. And then over here, this is a resource of type R1 that's been allocated to P1. It already has it. So arrows pointing out of a process are things that they want to acquire. Arrows pointing into a process are things they've already acquired. Okay, so let's move on to look at some more complicated uses of these. So I've kind of left these up here for reference, but now notice that if I have P1 wants R1, but R1 is held by P2. So P2 holds R1, P1 wants R1. There's only one of them available, so P1 has to wait. So in other words, worker 2 has the hammer, worker 1 wants the hammer, he can't get it right now because somebody has it, he's got to wait. You can think of this as like a library book. This guy's checked the book out of the library. He wants it, so he has to stop and wait for it to come back. All right, now over here, we have kind of a deadlock condition with a circular wait that P1 wants R1, but R1 is held by P2. P2 wants R2, but R2 is held by P1. They can never get out of this because they're always going to be stopped waiting for that resource that's never going to show up because the person they're waiting to put it back is also waiting on something they have. So there's a classical deadlock condition down there. Okay, so here's the idea. We want to perform this reduction of the resource allocation graph as follows. So in other words, remember that a resource allocation graph looks like one of these things. So we're going to perform this reduction as follows. First, if all the resource requests of a process could be granted, meaning the things are available or could be available to assign to them, then we can reduce the graph by that process. What does that mean, reduce the graph? That means essentially we assume the process finishes, we return all of the resources that it holds back to the system. Now, we continue that. We go through every process, eliminating ones we can, returning their resources, eliminate, return, until we get all the way down where no further reductions can be done. And if the graph can be completely reduced, then there's not a deadlock. We know there's no deadlock right now because everybody could eventually complete, and we could make it to the end where everybody did their jobs. Now, if a graph can't be completely reduced, then we know there's a deadlock. And not only that, but we know who or what processes, what set of processes are kind of involved in that deadlock. And we could do something now to recover from that. Now, one of the things to note is we'll have to do that reduction every time a resource request changes or a resource is returned. We have to say, so this isn't like a one-time thing we do. We constantly have to be saying, is the system in deadlock? What about now? Is it in deadlock now? Somebody requested something. What about now? What about now? And so forth. So we need to do that reduction repeatedly in order to know if and when the system gets into a deadlock condition. All right, let's look at an example. All right, so here's a little more complex example. We've got 4 processes, 3 resource types, and R2 has 2 individual resources of type R2. Now, remember, arrows out of a process are requests, arrows into a process are held resources, and right now you'll notice none of them have all the resources they need. So in other words, every one of these has a request. So P2 is waiting on R2, P1 is waiting on R1, P3 is waiting on R2, P4 is waiting on R3. Now, the question is, right now they don't have all the resources they need, but could any of them get all of the needed resources? So could P4? P4 cannot, because he needs R3, but R3 is taken. But P1 really only needs R2, so P1 could potentially get all the resources it needs. And P2 has these two, but needs one more, needs that one. He could finish. And notice P3 could get that one and finish because this one's not allocated to anybody. We could have P1, P2, and P3 could all potentially finish. All right, so let's go ahead and give it to P3 and have it finish. He only needs one thing. So let's give it to him, have him finish. So he picks that up, he finishes, and that means we can reduce the graph by P3. So in other words, we don't have to really wait for it to finish. We can just assume, hey, he could get everything he needs and be done. So let's assume he did that. And then we can reduce the graph by P3. So we reduced by P3, and now that one has been returned back, and now P2 could get it. So let's reduce by P2. So reducing by P2, he finishes, and now we have both of these have now are now available. And now P1 could get R1 and R2. He already has R3, and he could finish, so we could reduce by that. So now P4 or R3 gets freed up. P4 can now finish, and we can reduce by that. And so therefore we had no deadlock in that original more complicated view there, because all of them could potentially get their resources, could potentially complete. So there was no deadlock there. All right, let's look at another example here. So here's another example. 4 processes and 4 resources this time. 4 resource types, none of them have more than one. So can any of these complete? Well, P3 is waiting for R3, which is available. So P3 could get that R3, and then he'll have both R4 and R3, which are all that he needs. So he could complete. So let's reduce by that one. Now, are there any other ones that we could complete? Well, P4 could get R3 and R4, so we could reduce by that. But now we're to a point where we have this, and we cannot reduce this by anything. In other words, P2 is waiting for R2, but it's not available. P1 is waiting for R1, but it's not available. P1 could get R3, but that doesn't help with getting R1. So in other words, here's the circular wait we have here, holding on to these 3 resources. And so we have deadlock detected, and P1 and P2 are the ones involved in that deadlock. Okay, so deadlock detection, we have a way to detect when there's deadlock on our system. But what do we do about that? How do we fix that? Well, there are a couple methods here. And the only possibilities are to, if we go back, how do we break this kind of deadlock condition? Well, there are only really a couple possibilities. One would be to forcibly remove one of the processes or one of the resources from the process. In other words, all right, you're P2, you're holding onto the hammer, you're involved in a deadlock, I'm just going to take it away from you. And the other possibility is we just kill one of the processes, which is kind of like, it's we call this like deadlock recovery, but it's really a very harsh action we took. In other words, hey, these 2 processes are in a deadlock, I'm just going to kill one of them. So it's kind of like, hey, you have the hammer, he wants it, and you murder that person and take the hammer away from them. The good news here is that in operating systems, you might restart that process. If there's more than 2 processes involved in a deadlock, then you just pick one, kill it, see if the deadlock is still there, pick the next one, kill it, see if the deadlock's still there, and you kind of repeat that until the system recovers from the deadlock. Now, obviously, that's not ideal because processes were clearly starting to do something useful, and we have just killed them before they did that. The other problem with that and resource preemption is it might not be possible to preempt some resources, or it certainly might put the system in a state where something's kind of part-way processed or something like that. And restarting that process might not fully recover and might not do what we wanted it to do. All right, so deadlock detection. Notice that process of going through that, while it's a pretty simple process, it does have overhead. We have to do some computations to compute that. And it has to be done repeatedly. Anytime the resource needs change, something tries to allocate something or request something, or gets something allocated, we got to check for deadlock again and again and again. Now, an alternative approach to that is to use some sort of timeout-based resource allocation, where if something waits for a certain amount of time on something, then we throw an exception or kill that process or do something about that. Now, the idea there is if a lock or resource allocation waits longer than we expect, then we stop and report that there's a deadlock and then recover from it. But our recovery options are still kind of the same as they were before. Now, the problem with timeout-based systems is it gets rid of the overhead involved with kind of this resource allocation graph reduction process. But the problem with that is we don't really know how long we need to wait before timing out necessarily. So for example, does the operating system wait a tenth of a second or a whole second? The system could just be slow, and there might not actually be a real deadlock there. And so we could end up with some false positives where we end up killing a process when it would have finished. And we also have this problem of if we kill those processes while they're waiting, we have kind of this same problem we had before with this kind of half updated data or a system state that is partially updated, which could involve like a corrupted database or a file that's half written, and that could be bad too. Now, there's one third possibility here, and that's this kind of smart way of doing this. In other words, deadlock avoidance. It basically says, you know what? Allow all four conditions to occur, but let's be really careful and clever about how we allocate the resources. And one way to think about that is that we never want to grant a request if it could potentially lead to deadlock. Now, that sounds like a great idea. Like, in other words, we'll let everything play out as it will, but if somebody asks for something that could cause a deadlock, then I'm going to step in and say no to that process. But the question is, like, that sounds like this kind of AI system. How do we do that? So how would we ever set up a system to be intelligent like that with resource allocation? All right, so let's start off with looking at one way to do that. So first off, let's imagine each process has, when it starts up, it says, this is all of the resources I'm going to need. And it declares that at the beginning. So it doesn't have to allocate them all at once. So it's not an all or one allocation. It just has to say, these are the things that I could potentially need during the running of my process. It's not saying it might need them all at the same time, or it doesn't want them at that point. It says, hey, for future reference, these are the things that I'm going to need when I run. In other words, the processes state all the resources they might need before they actually request them. So they haven't requested anything yet. They're just saying, hey, operating system, this is what I'm going to need when I run this process. Now, what we're going to do is we want to look at the system in kind of one of three possible states. Safe, meaning it's not deadlocked, and there's no possibility of deadlock, even if all the processes got everything that they eventually would need or eventually are going to request. So that's a safe state. Unsafe is it's not deadlocked, but if everyone asked for all resources at once, deadlock could potentially occur. So in other words, if you were to imagine, okay, everybody told me what all the things they might need would be. What happens if they all took them all at the same time? Would that or could that result in deadlock? And then deadlock is obviously, a deadlock has already happened and it's too late. So to track this, we're going to use a few data structures here to track, and we're going to make a system that guarantees that we always transition from a safe state, where there's no deadlock and it's not a possibility of deadlock, to another safe state. So we're going to be very careful about how we allocate things to make sure we're always moving the system into a safe state after a request is made. All right, so let's look at those data structures. So we're going to have these four things that we're going to track. The existence list, which I'm going to shorten to EL, existence list. And that basically is how many of each type of resource exists in the system or is available. So you might imagine, let's say we have an embedded system. It doesn't have a really large amount of resources. So it might have a keyboard on it. Let's say it's maybe a point of sale system or something like that. It might only have 8 network sockets that it can use, and it might only have 5 file handles in the file handle table that it can open at one time. So this is a relatively small system. Now note that the same thing is true for something like a PC. There's a limited amount of files you can have open at one time. There's a limited amount of network sockets that are available. There's a limited number of some kinds of hardware that are available. But I made these small so it's easier for us to see how this progresses in our examples we're going to do in a second. So this is these are just example numbers. So in other words, EL, the existence list, is going to be 6. Actually, that should be 5. Let's go back. That should stop. All right, that should be 5, 8, and 1, not 6, 8, and 1. I'm the typo there. All right, now, so here the available list, and this is actually wrong too. This should be 2, 4, and 0. So the available list is how many of each type of resource is free. So with 2, 4, and the keyboard allocated, the available, nope, yeah, this is right if that were 5. So this, with 2 files open, that takes 2 away from 5, leaving 3. And with 4 sockets open, that leaves 4 available of 8. And with the keyboard allocated, that leaves no keyboards left. So this would be right given 5, 8, and 1. So 5 minus 2 leaves 3, 8 minus 4 leaves 4, 1 minus 1 leaves 0, 3, 4, and 0. So this is the only one that's wrong up here. Now, that we're going to call AL, the available list. And then current allocations, those, notice these are kind of global system level things, but these go with each process. So every process is going to say, here's how much I currently have allocated to me. And then the max allocations is what it had to state at the start of. That's how many it might potentially need later on. Okay, so let's go ahead and look at this. So here's an example. Let's say we have 5, 8, and 1 in our existence list. And our available list is 3, 4, and 0. And notice that means that 4 sockets are being used and 2 files are being used. And here's how they break down. So let's say we have 4 processes, A, B, C, and D. And there's CA and MA as a file. So current allocation for A, it has 1 file opened, 2 sockets opened, and it has the keyboard right now. But process B has 1 file open, process C has 2 sockets open. So that's the current allocation. But what they stated as their max was this could need at most 3 sockets, 1 file, 1 keyboard. This is never going to need a keyboard, but it needs 2 sockets. This needs 2 files. This needs 2 sockets and 1 keyboard. This needs just 2 files. So in other words, this is the max they could ever need. And you notice right now they're all below in their current or below the max need that they could have. So the idea here is if all processes suddenly requested the max, in other words, this one needed to open its 3rd socket, this one needed to open its 2nd file, this one needed to get the keyboard, this one needed to open 2 files. If they did all of that at once, could they all potentially finish? Is there some way they could finish? All right, so let's look at how we would do that. So is that previous state, is this state back here safe or not? It seems like maybe it's not, because you notice like, well, this guy's going to need the keyboard, but there's no keyboard available right now, so maybe he can't finish. So maybe there's no way they can't. But let's go through the process of figuring out if this state is safe. So the idea here is how much could each potentially request. So if we take their max and subtract their current from that, that'll leave kind of the request remaining for how many are left. So in other words, he has 1, 3, and 1 as his max, but he currently has 1, 2, and 1. So what does that result in? His need, his maximum need. Well, he already has 1 of these. He already has 2 sockets out of the 3, so there's 1 socket that he doesn't have. And then the keyboard, he already has it, so he doesn't need that. So his max additional need, the request remaining, is 0, 1, 0. And notice, what do we have down here? We've got 3, 4, 0 available. So note that in this case, and we do that for all these, so 2, 0, 0, he has 1. That leaves a maximum request remain of 1. This one, 0, 2, 1, 0, 2, 0. That leaves 1 keyboard that he still needs. And this request remaining, this one has 2, 0, 0. His current allocation is 0, so he needs 2. He needs both of them. He has nothing right now. All right, so let's focus on this first one, process A. So with process A, are there enough available for him to fulfill his maximum need? He needs 1 socket. There are 4 available. Yeah, he could finish. So we can observe in this case that process A, can get all of the resource. It needs 1 socket, and there are 4 available. So in this case, what we're going to do is we can update kind of the available list by assuming that process A finished, and then returned all of its requests or resources back to the available. So in this case, it currently has 1, 2, 1. So we're going to add that back to 3, 4, 0. And if we look at that, so 1, 2, 1 plus 3, 4, 0. So 1 plus 3 is going to give us 4. 4 plus 2 is going to give us 6. And 0 plus 1 is going to give us 1. So we're going to end up with 4, 6, 1 after we return these allocated resources back to the available list. So now we have 4, 6, 1. So let's go on. So now we have A has finished. So I just put like little dashes in here to show A is done. We don't have to worry about it anymore. But now let's say, can B finish? So B needs 1 file, but there are 4 available. So yeah, it can finish. So what we're going to do is we're going to do the same thing, and then we're going to return B's 1 that it has back. So now we get 5, 6, 1. So 1, 0, 0 plus 4, 6, 1. 1 plus 4 is 5. 0 plus 6 is still 6. 0 plus 1 is still 1. So we have 5, 6, 1, and now B has finished. So we're going to continue that process. What about C? So looking at C, can C complete? Yeah, it needs 1 keyboard. It already has its 2 sockets, so it needs just 1 keyboard. Well, so happens we have a keyboard, so we could grant that and then say C finished. And so now we're going to return those 2 current allocations back. So that becomes 8. So now all of the sockets are available. 5 of the files are available. 1 keyboard available. Well, D only needed 2 files, but 5 are available. So now D could complete 581, 200. This is all less than or equal to each of these. So this could complete. Now we return those back. And now notice we're back to 581, which is back to the existence list because everything is now returned anything. So that state was safe. That state could be completely reduced down to everything completing, and all of the available the available list is the same as the existence list. Everything is back to being available because everything completed. All right, let's look at one other example here. So this example, same processes with the same maximum needs and same current allocation. But what I'm going to do in this case is just change the resources that exist and those that are available. So in this case, notice the current allocation was the same, that I had 3, but now I only have 3 files that exist and 4 sockets that exist. So this is let's say a smaller embedded system. Still 1 keyboard, that's the same, but these got reduced. So now with 3 of these, you'll notice that the current allocation, 2 of them are already taken. A has 1 and B has 1. That only leaves 1 left. And for the sockets, A has 2 sockets open, and C has 2 sockets open, which since there were only 4, there are 0 left. And 1 keyboard, well, process A has that keyboard, so there's 0 left. So our AL is now 1, 0, 0. And our max allocations are the same as they before. So let's say, is this state safe? Well, let's go through the same analysis that we did before. So the same analysis we did before, we're going to come up with a request remain by subtracting each of these. So A has 131, or needs 131 at max. It has 121. That leaves only 1 socket that it needs, so 0, 1, 0. And in this case, B has 200 as its max. Currently it has 1, so it only needs 1 extra F, nothing of the O2, so 100. And then 021, 020, that leaves 001. 200 is the max, nothing is allocated, so 2. So this is what our request remain looks like. Can any of these finish? Well, clearly the only one of these that can finish right now would be process B. It needs 1 file there's one file available. So let's go ahead and grant that request. So B can complete and return all resources. That'll result in an A being 200. And here we have A as 200. And now D needed 2. So D could complete and return all resources. So D is going to complete, return all resources. But notice it didn't have any here in its current allocation to begin with. So that results in AL still being 200. In other words, it took those 2, it could complete and put the 2 back. So we're still at 200 here. And so now we have this. We've got AL of 200, but notice that the request remain is the process A needs a socket, and there are none. And process C needs a keyboard, and there are none. So neither A nor C can do anything and complete. So that system could deadlock. It doesn't mean it will. It just said if they requested their maximum allocation, there is not enough resources for them to all necessarily complete. Now, if they just acquired it and released it, we could get where it works correctly when we run it. But there is a possibility that the sequence could go where this one has all of the things it said it might need, and this one has all of it, and this one has the keyboard that this one needs, and this one has the socket that that one needs. And now we have the possibility of ending up in this circular wait. So since that system could deadlock, it's therefore considered unsafe. Now, the way deadlock avoidance works is, and there's a misspelling of Dijkstra there, but that leads us to Dijkstra's banker's algorithm. And Edsgar Dijkstra, super smart computer scientist, we saw him before as the inventor of the semaphore, but he also came up with this. He was very big in the kind of concurrent systems area, but he came up with this banker's algorithm. The reason it's called the banker's algorithm is you don't want to have too many loans out to cover the maximum need of somebody who could come into your bank and cash something in and need that. So his idea was, if you think of it like a banker, they need to be careful to have enough cash on hand to cover certain types of projects for the loan when people draw down that loan, because you don't want to have all these projects, none of them can complete, and then you're stuck not being able to make your money back because they can't finish their projects that they need the money for. So his idea was basically like this. So start off with some process, we call it Q. And that process makes a request. And now what we're going to do is we have the available list and the current allocation list. Available list for the system, current allocation list for a certain process, in this case Q. So what we're going to do is we're going to make new versions of those, AL prime and CA prime. And now we're going to go ahead and update AL prime and CA prime as if that request was granted. So we're going to come up with a new available list of what the system might look like if we granted that request. We haven't done it yet, but we're going to look at what would happen if we did. And then we're going to say in this process, we're going to update its current allocation list. That should be CA there. So we're going to go ahead and allocate those two. And then the next step that we're going to do is we're going to compute their maximum request remaining as REQ prime, which is the maximum allocation for the process minus its current allocation prime, the one that would happen after that. And then we're going to act as if all processes are requesting maximum resources. So we're going to do what we did on those previous charts. And we're going to say, if using those three, if there is some way to reduce that where they could all finish, then that is going to result in a safe state. If using those three, we haven't changed anything yet. Remember, these are the prime values. If using all those three and it couldn't finish, then we have an unsafe state that where deadlock could happen. So what happens here is if we say if it could be reduced down to where they could all finish, then that's safe. So we're going to go ahead and grant the resource, and we're going to update the available list to the one we imagined, the CA for that, the current allocation for that, as the one we imagined, and then we grant the resource request. Now, if it turned out that this resulting state was unsafe, we reject the request and say it's denied. Even though we might have the resource, we're still going to deny it, and we're just going to leave AL and CA unchanged. And when we deny that, that process is going to come back and have to request it again later. But the idea here, it's really kind of a brilliant solution. It's very easy to code, very simple to understand. And you notice how easy the math was back here. We're just doing some subtractions of things in the one table versus another, and then saying, well, yeah, that's less than that, so let's get rid of that one and return its thing. So it's very easy, very quick to implement, but it leaves all four conditions there. But it says anytime anybody requests a new resource, I'm going to go through this process and check and imagine what would happen if the thing I imagine happening is unsafe. I say no. If the thing I imagine happening is safe, then I say yes and update my system to match that reality. Now, there are a couple problems with this. A process might not know or be able to state its maximum resource use at startup, which could be a problem here. And so the other problem is we might deny some requests to preserve safety that we could otherwise grant. And if we do that, we have a process waiting on a resource we have available, and we're saying no anyway, just to preserve safety, which could hurt our resource utilization and slow some processes down unnecessarily at the expense of ensuring safety. The other part of this that's important to note is that what this is denying is it's not denying getting us into a deadlock condition. It's denying putting the system in a case where it could potentially get in a deadlock situation. In a lot of cases, it might be highly unlikely deadlock would ever happen, even if we just allowed them to run however they ran. And so we might be unfairly slowing down certain processes to preserve safety, but that could be worth it depending on the kind of system we're designing. Okay, Livelock, I'm just going to mention that quickly. Livelock, which I have here, is Deadlock's ugly cousin. Notice that with the dining philosophers, let's think about what Livelock would be like in that particular problem. So let's imagine we try to fix that by saying, okay, everybody picks up their fork on their left. They look to their right. If there's not a fork there, they put the one on the left down and they wait exactly a second and then they try again. And you might think, well, in that case, they're not holding on to the resource while they're waiting. They're putting it down and then they're waiting a certain amount of time. But you can imagine there we can still wind up with a situation where they all look to their right. There's nothing there. They put the one on the left down. They wait a second. They pick the one on the left up again and look to the right. There's nothing there. And you can imagine them all being synchronized, all putting them down, all picking them up, all putting them down, all picking them up. And they're just going to keep doing that over and over again. Now, Livelock can be considered worse in some cases than deadlock because not only are we locked up and not going to make progress on our problem, but we're also consuming CPU resources while we're doing nothing. So we're kind of like zombies, like imagine the philosopher sitting there like picking things up and setting them down over and over again. And they're never going to make progress on eating their meal when doing that. And so that's kind of what Livelock is about. It's very closely associated with deadlock, but you have active consuming of resources rather than passively being blocked. Okay, well, that's all for today. And you might look for the assignments that are going to get posted. I'm probably going to post an assignment on deadlock. So look for that. And one of the things, we're starting to run out of time here. I'm clearly not going to get through everything that I wanted to because of the lost week, and it's a little more difficult to cover things in this format than it is in a live face-to-face format. But I do still want to next week get to a couple more topics, and then we are going to have a final exam in here. It'll be whenever the final exam schedule says it's going to be. So look for those upcoming assignments, and then stay safe, and I'll see you next week.